So I'm Damian Stefaniuk. I work as a research scientist at MIT Sydney Environmental Engineering Department, at the same time at MIT Concrete Sustainability Hub and MIT Electron Conducting Hub. I'm working on multifunctional concrete that can both carry load and store electrical energy. So lithium-ion batteries face several critical issues. First, lithium, cobalt, nickel, main minerals used to build those batteries are finite resources. So we have extraction, which is resource intensive, leading to environmental degradation. Then global demand for energy storage grows every single year. So particularly for electric vehicles and renewable energy system, relying just on lithium-ion batteries alone could result in shortages. And finally, we have safety risks. We have potentials for overheating, fires, and some areas are forbidden to use lithium batteries. And second, there is a recycling process. Batteries usually last 10 to 15 years or less, and we have to dispose the material, recycle it, and so on. So those technologies are still inefficient and undeveloped. As a result, I wouldn't say we have to get rid of lithium-ion batteries, but we have to help them out for the transition to renewable energy. Supercapacitors are energy storage devices that charge and discharge much faster than traditional batteries, but they have the same function to store electrical energy. And they have different architecture than batteries. They are based on double layer effect, so they store energy electrostatically, while batteries store energy based on chemical reactions. So in general, supercapacitors can charge faster and they can last much longer since there are no atomic intercalations, but at the same time, their energy density is lower compared to batteries. And in our case, what we do, we replace electrodes used in supercapacitors, since supercapacitor is composed of two electrodes separated by separator and also in electrolyte, so ions can go through. In our assembly, we make electrodes, those two electrodes, negative and positive, out of conductive concrete. A regular concrete mix we modify by addition of carbon black that creates conductive material and can act as those electrodes. So concrete batteries could have potentially wide-ranging future applications since we've been using concrete for thousands of years and all our infrastructure is built out of concrete. One of key areas is renewable energy storage. You can imagine any part of your home like foundations, concrete slabs, walls, columns, and so on, that they do not only carry load and create our structure, but also can store renewable energy, for example, from solar panels installed on your roof. There are also other applications like all infrastructure around, like concrete bridges, concrete roads, for electrical vehicle charging stations that could integrate our product. So, as you mentioned, it's a quite new technology. So, therefore, there are multiple obstacles we are facing. Many of them we have already solved, but still there is issue with scalability. We have to still translate lab-scale prototypes into those full-scale applications to create our whole environment and basically incorporate our material and change design into existing solutions. Second is challenge we are facing, it's energy density. We still are working on increasing the energy density of our material. And finally, durability. Durability is an issue because concrete structures are built to last decades. We do not wish to replace our foundation after 15 years to just restore battery. So we are making sure that energy storage functionality remains effective over time and the lifetime of our existing structures. So each day we try to push the technology forward. Instead of running a fan and charging an iPhone, we want to, let's say, power a laptop, power other electronic devices that require much larger energy density and so on. So each day we are trying to build something bigger and bigger. At the same time, we are working on, for example, rheology of this material, how to make it adaptable for different concrete scenarios. That's actually a very interesting question. But in general, at school, in high school and so on, I was always drawn to technical subjects like math, physics. And then beyond that, my inspiration, I would say, to engineering came from my father. So he worked as a construction worker abroad and returned to my home country to build our family home and eventually start his own company. So I was seeing his work ethic and ability to create something tangible with his skills deeply inspired, that later on deeply inspired me to pursue a career where I could use my technical knowledge to solve real world problems. So I feel that engineering felt like a natural fit for combining my strengths with the desire to make an impact.